All right, everybody. I had a request to please work out some or all of the problems in our practice test on a video so that you can follow along if you need help. I highly recommend that you take a look at the practice problems first, work as many as you can all by yourself. Check the solutions. I've uploaded those into this week's module. So check the solutions I worked out by hand so you can see if you agree with them or not. And then if you're still having problems, hopefully this video can help you see what you're missing or what you need to do to move forward. Okay. Um, so without further ado, I'm looking at the practice questions, and number 1 says, is the following a function? And why or why not? So it's y equals x cubed plus 5x minus 9. Okay, so if you remember, the rule for function is there's one about the graph. Well, we don't have the graph of this one. If you wanted to, you could stick it on your graphing calculator and see the graph. It's going to look something like, it's a cubic, so it's going to look something like this. Okay. But and you could do the vertical line test and say, yeah, that's a function, no problem. But what you can't do is you can't. So if you want to do vertical line test, you can, but you have to give me the graph. Okay. I didn't give you a graph, so you can't say vertical line test. All right. So here, though, the nice thing is it's already solved for y equals, and I need to just use that idea of what is a function. So if you remember, every input gets one output. Not 2, not 3. 0 would be okay. So let's say at most. 1 at most. All right. So whenever I stick in a number here, the question is, am I going to get more than one y value coming out? And whenever I look at this, I say no. And the reason why is I would only get 2 y values if, say, this was a plus or minus out here. Like a plus or minus a square root guy, that guy gives me 2 y values, right? But here, let's just pick our favorite number. I'm going to say 1 because it's going to be easier for me to work with. Y equals 1 to the third plus 5 times 1 minus 9. 1 to the third is a 1 plus 5 minus 9. That's 6 minus 9. That's negative 3. Okay. So here we say, okay, every time we plug in one x value, we only get out one y value. Now, this is only one example. Okay, there's lots of examples, but what we need to be worried about is if there were a plus or minus out here, and there's not. So that's the idea there. We only get one y value for every x, and we know that because it's not a plus or minus. Okay, number 2, does the following graph represent a function? Now I give you a graph. Okay, and the graph looks something like, you can look in the paper and see it, but it looks something like that. Okay. And this one, if I give you a graph, would absolutely be very simple for you to just look at and go, are there any spots where I would draw a vertical line and hit the graph more than once? And the answer is no. Anywhere I draw here, I'm only hitting it once, right? So, oh, sorry, that was a yes up there. Okay. This one is also yes, a function, and you need to give me the reason because it passes the vertical line test there is perfectly legit. Okay. So up here it is, but you need to give me something like every input gets one output or something like that. Or like I did, give me an example. Something that lets me know you know why this is happening. All right. Number 3, find the average rate of change of the function. And it's f of x equals 3x squared minus 1, and it's between x equals 1 to x equals 4. Okay, remember this idea of average rate of change is just exactly the same as just exactly the same as whenever you have a slope. Okay, so we use that formula. The slope formula normally that we would use is y equals, I'm sorry, m equals y2 minus y1 over x2 minus x1. Or for AROC, average rate of change, it looks a little bit different. F of x1 minus f of x2. I'm sorry, I switched those on you. Let me switch that back. F of x2 minus f of x1. It doesn't really matter as long as you keep them straight, right? Over x2 minus x1. I was just trying to line these up with what I already had there. Okay, so the idea being the functional value whenever I plug in x2, well, we know that the functional value is your y value. So those are the same. It just looks a little bit different. But basically, even though this is quadratic, we are going to use the slope formula to find out what's going on between these two things, right? So here we go. I need to know the point. So I usually tell people something like, find the point, okay? When x is 1, we go 1 squared is 1 times 3 is 3. 3 minus 1 is a 2. So this point is 1 comma 2. And 4, whenever I put in 4, let's do that again. X squared would be 16. 16 times 3 is 48. 48 minus 1 is 47. Okay. So that becomes kind of a big thing, big number, but we can deal with. So all we're going to do is use these to go into the slope formula. And again, you can use AROC or you can use the slope formula. And the work out the same. M equals take your y value minus your other y value. And if I started with this guy as y2, remember to start with this guy as x2. So 4 minus 1 on the bottom. Okay, so 47 minus 2 is 45 over 4 minus 1 is 3. Okay, 45 is actually divisible by 3, so I can reduce this and make it a little bit nicer. 15, right? If it was not going to divide evenly, you could leave that. I'm not too picky about you leaving things as improper fractions. In fact, sometimes I say leave them alone because otherwise we make little mistakes. All right, that's that. Set the window on your graphing calculator from -5 to 5 for both the x and the y. Graph your function, find the x and y intercepts, and determine the local minimum or maxes and local minimums. Okay, so I think whenever I wrote this problem, I just wanted to kind of make sure that people knew how to use their calculators a little bit. I'm not actually going to require you to set a window or anything like that on the exam, so don't stress out about that. But we've got x to the third, right? And then I'll come out of there because I don't want to be in the exponent anymore. X to the third minus 2x squared. Okay, that's the equation that I gave you. And I'm going to go ahead and set my window just so we can see -5 to 5. We're going to use the scale of 1 and then -5 to 5. Let's still, oops, not a negative. Eek. Delete. Okay. And then still let's use a scale of 1 and graph this guy so we can see it. There it is. I think the reason I said on the question, to set the window is because I wanted you to be able to zoom in and really find it. Okay. There looks like this is going to be both an X and a Y axis. I'm sorry. X and a Y intercept right here on the X axis at the origin. And then here it looks like we're going through the point 2, 0, right? We're going to double check and make sure that's true. But I think we're going to have x-intercept, y-intercept at the origin, and then 2, 0. So let's see how that looks. And then it says, what else did it say? Find the x-intercept, y-intercept, determine the local maximums and local minimums. Okay, so we're going to do that real quickly. Here comes my problem. It was y equals x to the third minus 2x squared. And whenever I look at this, I say, oh, okay, look, they have an x squared in common. I'm going to factor that out. And when I factor an x squared out of here, I'm left with an x. And whenever I'm factoring an x squared out of that, I'm left with a minus 2. And so this is the factored form. In order to check it, remember you should be able to multiply that through x to the third minus 2x squared and get the same thing you started with, which I can. Okay. And then remember the process for finding intercepts. If you want the x-intercept, you plug in, what is it? 0 for y. And if you want the y-intercept, you plug in 0 for x. So remember, it's always the opposite variable, right? And whichever intercept you want, you plug in 0 for the opposite variable. Okay, so for instance, I'm looking right here. I've got y equals x squared times x minus 2. If I want to start with the y-intercept here, scoot that just a little bit, then I'm going to plug in x equals 0. So here it is, y equals 0 squared times 0 minus 2. Well, 0 squared is just 0. And anything times a 0, that's going to be, so this is going to be, it's 0 times negative 2, but anything times a 0, that's just a 0, right? So sure enough, we do have the point x was 0, y was 0, right? Okay, so that is a y-intercept. It also happens to be an x-intercept, right? And we'll see it again here in a second whenever we do the x-intercept. So just be aware of that. All right, so how do we do that for the x-intercepts? Again, plug in y equals 0. So this part over here, 0 equals x squared times x minus 2. And remember the old rule, if you set two things multiplied equal to 0, one or the other or both of them must be equal to 0. So we split this up and we said, okay, so x squared equals 0 or x minus 2 equals 0. And that's something that always happens. We always do that if we have two things multiplied equal to 0. Okay, so don't say always all that often, but it does happen sometimes. Square root both of these. Okay, x equals plus or minus the square root of 0. But what do we think about square root of 0? That's just 0, right? And then what about 0? Is it positive? Is it negative? Can I do plus or minus? It doesn't matter, right? That's just 0. So what we see here is this actually ends up being a solution twice because it works for the plus guy and it works for the negative guy, right? If you remember, this guy's biggest exponent is a 3. We should have at most 3 solutions. Here are 2 together. So it's 0 and 0 basically. And that's why we see it's here as an x-intercept and it's here as a y-intercept. And that's why when you look at the graph, it kind of bounces right there whenever you hit the x-axis. Okay, I'll show you that again in a second. Solving this one, add the 2 over x equals 2. Okay. So that would be 2 comma 0. Hey, that's what I thought I saw in that graph, which is good. I like it. Okay. So we do have 2 x-intercepts here. Technically, there's 3. There's 1 working over here. Okay, and this is what I meant by it bounces. Because it works an even number of times, we've got 0 coming out twice here, positive 0 and negative 0, but those are just the same thing. Okay, because that's a solution twice, it bounces, comes up, touches the axis, and comes back down. Okay, but the 2, x equals 2, that only happened once, right? I didn't have a plus or minus in there. Okay, and when I have that happen an odd number of times, it just goes right through. Okay, so that is correct. Those are my x-intercepts and my y-intercepts. And the last part of this thing said local minimums and local maximums. So remember, local means just right there in that area. So right here in that area, is the 0, 0 a max or is the 0, 0 a min? We know it goes higher here, but we don't care about there. We just care about right there in that area. And in my head, I hear you saying, it's a maximum, Dr. Webster. And what about here? Is that a min or a max right there where it comes down here? It's a minimum, Dr. Webster. That's what I hear. Okay, so that's exactly what's going on there with the maxes and the mins. Okay. And the reason we look at that now, the maxes and mins, and we want to know what's happening here, like this was a cubic, right? So how many turning points at most do I have? The degree is a 3, so at most you have 3 directions. Okay, 1, 2, 3. Yeah, we got that. And that means at most you have 3 minus 1 or 2 direction changes. 1 there, that's a turning point, and 1 there, that's a turning point. And when you see those turning points, those are where you're saying, hey, we've got maximum spots and minimum spots coming out. And the reason why I care about that right now is because whenever we get into the calculus, which is test 2 material, so it's coming fast. You can only have so much algebra review, right? Now we got to get on into the derivatives and stuff. And when we do that, we're going to care a lot about maximums and minimums. That's going to really come into play. All right. So just FYI, it's all, I promise when we get to test 2, you'll be like, oh, that's why she wanted us to be able to factor. Oh, that's why she wants us to be able to see maxes and mins. It's all going to kind of come together as we look at that calculus stuff. Okay, enough with the threats about calculus. Right now we're doing algebra, intense algebra review. Okay, number 5 says find the x and y intercepts and the local maxes and mins. It's basically the same kind of problem we just did. It says f of x. I'm writing y. It's fine. It just tells me it's a function. 2x squared minus 5x plus 3. There's my equation. It happens to also be a function. I know because it told me f of x, so it's a function. And they want me to figure out x-intercepts, y-intercepts, and local max and min. This is the same kind of problem, but earlier, this one was pretty easy to factor, right? I just pulled out the x squared. It was just a binomial, no big deal. This guy is a trinomial, and again, if you can't factor this, you're gonna have to go, oh man, I'm gonna have to work on that and figure out all the quadratic formula and that kind of stuff, right? And honestly, we don't really want to do that if we don't have to do that, right? So let's not do that. Um, I'm gonna factor. I know that it's gonna be 2x times x gives me 2x squared. I need something that's going to multiply here and add there and give me a -5. And by the way, factors of 3 are only 1 and 3, but it's positive. So a negative times a negative is going to give me a positive, right? Okay, so let's see. I need a 3 here and a 1 here. 2x squared minus 2x minus 3x, that's minus 5x in the middle, plus 3. And I put that factoring review on. I also put an exponent review on in its own little module for you to look at. And I really mean for you to be able to factor, okay? I did this by trial and error, just kind of whipped it out real fast. If you can do that, great. If you have to use the AC method that I showed in my videos, that's great. If you're a box factor by box method, that's fine by me. What I really don't want you to have to do is go back to quadratic formula over and over and over again. It just takes too long. Like I did that in, I don't know, 5 or 10 seconds, right? So if you have to go back to quadratic formula, you can do it, and I know you know how to do it. It's just going to take you a lot longer, and that means it takes you longer to take the test. So just FYI, try to get that factoring down. Okay. I'm going to say x-intercept first. I don't know why. I just want to. So I'm going to plug in y equals 0, right? So 0 equals 2x minus 3 times x minus 1. And we said take each one, set them equal to 0. 2x minus 3 equals 1 equals 0, or x minus 1 equals 0. Solve this guy real fast. Show me as many steps as you need here. 2x equals, add the 3. Positive 3, divide by 2 to get the x by itself. X equals 3 halves. And yes, I know I'm going through this a little faster than I did whenever I did the teaching videos, but that's because this is supposed to be review, and hopefully you know how to do this, okay? Hopefully you can go right along with me and do the steps as I'm going, or you've already done it before you sit to watch this video. Okay. This one, it's got a minus, so I'm going to add 1 to both sides. X equals a positive 1. Okay. So these are my x-intercepts where I plugged in y equals 0. So remember, that's the point 3/2 and 0 and the point 1 and 0. I made an issue out of it whenever we were dealing with this information. You need to either give me x equals like this, or you need to tell me the coordinated pair. Give it to me as a point. Okay. What you can't do is just say 3/2 and 1. I see that a lot. People will be like 3/2 and 1. And do I know what you mean? Absolutely. But it's improper math notation and you're not going to get full credit for it. Okay. So I made an issue out of that when we did the teaching video, and I'm coming back and reminding you right before we do the test, don't do that. Okay. So that's x-intercept. Y-intercept is plug in x equals 0. So let's do that real fast. Up here, it's probably easier to use the original. Y equals 2 times 0 squared minus 5 times 0 plus 3. I'm just plugging in x equals 0. These two guys go away and I get a 3, right? So that's the point 0, 3. Or again, if you want to say y equals 3, I'll accept that. It's actually better as a coordinated pair. Okay, so there you go. What about this guy? He was actually quadratic, right? And he's actually got a leading coefficient of a positive 2. So remember, that's a happy face. Positive things make us smile. Okay, he looks like a parabola like that. And so his vertex, we can actually find the actual vertex without using our calculator. His vertex is going to be what? Max or min? Min, Dr. Webster. Yes. So there's a minimum at x equals, and remember, it's negative b over 2a. That comes out of the quadratic formula. It's part of it. I didn't do this, but here a equals 2, b equals negative 5, c equals 3. I'm just kind of out of space there for those things. But there you go. We can find them. So whenever I go to do negative b over 2a, I say, hey, there's a negative in the formula, and the b is a negative 5. 2 times the a is a 2. Okay, so a negative and a negative is a positive. 2 times 2 is 4. We've got a minimum at x equals 5/4. That's the x value, right? And then we want to know what the total point coordinated pair here is. If you want to know that, how do you do that? Remind me. And I'm hearing in my head that you go back and plug in 5/4, right? So again, let me come here. Y equals 2 times 5/4 squared minus 5 times 5/4 plus 3. That's how you figure out what the y value is, right? Plug in your x value. Absolutely. All right. So y equals 2 times square this guy. It's 25. Remember, when you're squaring a fraction, it's square the top. 25 times 5 is 25. Square the bottom. 4 squared. 4 times 4 is 16. So 25 over 16 minus, and I'm going to go ahead and put a 1 here so I can go top times top. 25 over 1 times 4, 4 plus a 3. And then one more thing here. This guy can be a 2 over 1. So when I multiply that out, I'm going to get 50 over 16 minus 25 over 4 plus. I'm going to go ahead and write him as a 3 over 1 because I can see where this is headed. I've got a couple of fractions that I'm adding here. Again, you can do some of this on your calculator, but you really have to show me enough work that I know that you know where this answer is coming from. Okay. So looking at these, I've got denominators of 16, 4, and 1. The least common denominator here is a 16. So I'm going to get common denominators so I can add and subtract. 50 over 16. This guy already has a 4 down there, so to make the denominator be a 16, I need to go 4 times 4 to get to the 16, right? And remind yourself, anything I do to the bottom of a fraction, I have to also do the top of a fraction. So this is 100 over 16. And then same thing here. To get to a 16, I have to go 1 times 16, which means this is going to be 3 times 16, 48 over 16. Okay. Sorry. It's kind of running together a little bit there. Let me do that. Okay. So it's those fractions in there messing me up. 50 minus 100 is going to be a negative 50 over 16. Remember that rule. Once you have common denominator, all you have to do is add or subtract the tops. Okay. Plus 48 over 16. Well, a negative 50 plus a 48, the rule is when you have numbers that are opposite signs, you subtract and take the sign of the bigger number. So this is a negative 2 over 16. And whenever I get all the way down here, I say y equals, that will reduce negative 1/8, right? Okay. And if you remember, we're looking for the vertex, so that is the y value. The x was 5/4. The y is negative 1/8. There's my vertex. Absolutely. Okay. And as a reminder, we said he's a minimum, right? Because this is a happy face. So he's at the bottom of the parabola. All right. Cool. Everybody remembering all this, I hope? I know. Okay, 5. Number 6 says sketch the graph of the function by showing all intercepts. Sorry, I lost my page. And the proper end behavior. P of x equals. Remind me what that P of x means. In my head, I hear you saying that means it's a polynomial. Okay. X plus 3, 2x minus 1, x minus 6. If you copy stuff like that down, please make sure you double check because that's where I make most of my mistakes. Okay, so I just know. Okay, so this is a polynomial that tells me that there's not any crazy fraction exponents or something like that going on with it. And we should have real numbers as our coefficients. That was the definition of polynomial. That's what P of x means. If you don't remember this one because it's already factored out for us. If we were to multiply all that together, it would be an x to the third, right? X times x times x would be an x to the third. So this degree of this guy would be a 3. Okay. And they're all positives. So if you remember, that means it's a cubic. And the graph looks like an S-curve, right? Something like that. Okay, it might bounce around a lot or not as much, but it's going to look something like that. Okay, so just a reminder of what we're dealing with here. Now, it said we're going to graph this guy by finding the intercepts and the proper end behavior. Okay, I know this is my end behavior. It's going down and to the left and up and to the right. Remember, ends means way out here on the ends, not what's happening in the middle. Okay, so it looks like that. It's climbing overall from bottom to top because it's positive, right? Positive, positive, positive. All right, so positive times a positive times a positive of a positive. But whenever I go to do my intercepts, it's the same process as what we've been doing the last 2 or 3 questions. 0 equals x plus 3, 2x minus 1, x minus 6. But because it's already factored for me, it's kind of nice. We didn't have to do that factoring process. We can just say either x plus 3 equals 0 or 2x minus 1 equals 0 or x minus 6 equals 0. Okay, so these are not hard to find. X equals negative 3. Add the 1 over 2x equals a 1 or x equals 1/2. Add the 6 over x equals 6. Okay, we've got 3 x-intercepts. The points look like this. -3, 0. 1/2 0, and, oh, sorry, 6 0. Okay. I'm trying to remind you, you either have to give it to me like an equation, x equals 6, or you have to give me that coordinated pair. Okay, so those are my x-intercepts. I need my y-intercepts, and that just means go in and put in 0 for x, right? So let me come back to this factored form. It's 0 plus 3 times 2 times 0 minus 1 times 0 minus 6 when I plug in 0 for x. So here we go. That's just a 3. This is a 0 minus 1. And this is a 0 minus 6. Okay. So real quickly, I've got a positive times a negative. That's a negative times a negative is a positive. So be careful with that. This is going to be positive. 3 times 1 is 3 times 6 is 18. Okay. And again, remember that was equal to my y value, right? Okay. P of 0 or y. Okay. So y equals 18, or this was plug in 0, get out 18 for the y value. That's my coordinated pair. All right, so here are my intercepts. I'm supposed to be graphing this sucker. You can stick it in your calculator and see how beautiful it is on the graphing calculator to check us, but let's just do this real quickly. I have an x-intercept at -3, 0. Right there he is. I have an x-intercept at 1/2 0. It's not a great scale, I'm sorry, but it's where I am. Okay, so 1/2 is gonna be right in there, something like that, and I have an x-intercept at 6 0, which is way out here, okay? And this just to make sure we're aware, the y-intercept was 0, 18. That's gonna be way up here. I'm just gonna put an 18 here. I'm not gonna sorry. I said I wasn't going to, but you get the point. Yeah, because I didn't have enough space, sorry. Okay, so something like that. Just pick a spot. It's 0 on the x's, 18 on the y's. Okay, and we know again that this is a cubic and it's rising, so it looks like that. So the graph of this guy is going to go through all those points. And this is just a sketch. It doesn't have to be perfect. Um, It might go way down here at the bottom. This should be close to our maximum, but I don't know. It's just an or y-intercept. It could go something like that, right? And be coming back down. So it's just a sketch to get a general idea. It does not have to be perfect. And again, if you want to plug that on your calculator and then sketch it out, that's fine, but you do have to do all the work we did. If it says find the x-intercepts, find the y-intercepts, you have to do all that to tell me what's up. Okay. Just making sure everybody's aware. I hope you're good with that. Number 7 says you've got a polynomial, f of x equals, and it's x times 3x minus 1 squared times x squared minus 4 to the third. And it's a little bit tricky, so we're going to play with it. It says find the degree. Okay, so let's make sure we're all on the same page here. Okay, this is x to the first. This is x to the first, but that x to the first is being squared, right? And remember your exponent rules. That means we're going to multiply those, right? The biggest degree for this guy right here, 3x minus 1 times 3x minus 1, that's what it means to square it, right? Would be whenever I square this first term, 9x squared. So the biggest degree right here is a 2, and that's because you multiply these, right? That's the exponent rule. If you're not sure, go look them up. I put that exponent review on, okay? And similar things happening here. This guy's degree is a 2, but he's being raised to the third power, which means if I wanted to write that out, it'd be like x squared minus 4 times x squared minus 4 times x squared minus 4, okay? And when I multiplied those three things together, that would be 2, 2, and 2. Here I would add them, because they're multiplied. But here it's a power to a power. You multiply them. Okay, so either way, 2 plus 2 plus 2 up here, that's a 6, or 2 times 3, that's a 6. So make sure you know those exponent rules. Okay, but here we go. We had a 1 here. Degree equals 1 times, this I said was going to be a 2, and this we said was going to be a 6. Okay, 1 times 2 is 2 times 6 is 12. Okay, so because you're multiplying all those things together, right? Okay. So I'm so sorry. I just lied to you. We're adding them. Okay. So we multiply here. I'm so sorry. We multiply here, but then I add them together. So 1 from this guy plus a 2 from this guy plus a 6 from this guy. So 1 plus 2 is 3 plus 6 is 9. I'm sorry. That just for just a minute I wrote it as multiplication and I just did it. I just multiplied them out. Okay, so determine the solutions and their how many times each is a solution. Okay, again, this is the process of looking for multiplicity. So the solutions are take the whole thing and set them equal to 0. Remember, we also call this the x-intercepts. We've done this lots of times now. So x equals 0, or 3x minus 1 squared equals 0, or x squared minus 4 cubed equals 0. This first one is a done deal. He's easy. Yay, x equals 0. But then remember here, we have to deal with this one repeatedly. How many solutions should come out of this second little term that I've got set equal to 0? How many did we say here? 1 times 2 was 2 solutions here, right? So whenever I do this, some stuff happens. 3x minus 1, how do I get rid of the square? Square root it, Dr. Webster. And don't forget your plus or minus, right? The 3x minus 1 drops out, but then I've got this plus or minus square root of 0, and we already talked about that even in this video. So square root of 0 is 0, plus and minus do not matter to 0, it's just a 0. So again here, whatever the solution is, we're going to see it doing double duty because it's the positive guy and the negative guy on the square root of 0. I think that bugs people sometimes. I think it's a 1/3. X equals, because I added it's a positive, 1/3. And it's a double solution, right? Double solution. Okay, or it works 2 times. Okay, that's what's happening there. And it's because of this square root of 0 that just kind of went away. Okay. And then here, this guy should be a solution. We should have 6 solutions technically coming out of this guy. We said that here, ups here, we multiply. He's going to give me 6 solutions. I think we're going to find that some of them double up, and that's fine, or triple up may be the case here. I'm going to get rid of the cubed root or the cube here by taking a cubed root. But what happens is the cubed root of x squared minus 4 cubed, the cubed root and the cube are opposite operations, so they will go away. And what happens over here? Cubed root of 0, it's just 0, right? So that just kind of goes away. So what I've got here is x squared minus 4 equals 0. Oh, that's just a square, right? I can add the 4 over, take the square root. When we do that, we do the plus or minus 2. Square and the square root go away. X equals the plus or minus. What's the square root of 4? I think I just said it on my own. Square root of 4 is 2, right? Okay. So what's happening here is from inside of here, I'm getting 2 answers, plus or minus. But we also know that each of them was a cubed answer, right? So x equals 2 So triple solution. Okay. X equals -2 is also a triple solution. Okay. So that's what's going on here. So when I think about it this way, the 2 works 3 times, the -2 works 3 times, the 1/3 works 2 times, and the 0 only works 1 solution, 1 time. Okay. But when we talk about these multiplicities or how many times they are solutions, hey, it works out. 1 plus 2 is the 3, and then 3 and 3 is the 6. So 3 plus 6 is indeed, where was it here? 9 solutions. Good deal. So remember, at most, I get the number of real solutions that the degree adds up to. The trick here is all of these are indeed real numbers. If I had imaginary numbers, then that could take out a couple of solutions. We haven't really dealt with imaginaries much in this class, but they're out there. So that's why we say at most you get 9 real solutions here. All right. I think there's one more that's similar to this, but maybe it's just kind of about polynomials and stuff. But maybe it's just a little bit of a reminder. So here we go. 8 says, for the polynomial function p of x equals x to the fourth minus 16, determine the degree. Okay, what is it? Degree equals 4 because that's the biggest exponent. Yep, degree equals 4. Determine the solutions and their how many times each is a solution. So again, take this guy, set it equal to 0, find my x-intercepts. The problem with this is a difference of squares, and it will factor x squared plus 4, x squared minus 4. Okay. I just said we hadn't done much with imaginary numbers. The problem with this is that this x squared plus 4, you're not going to have real solutions. So what happens is you set it equal to 0, and then you solve for x by subtracting the 4, right? Let me just show this work. Okay. X squared equals -4, and now take the square root of both sides, plus or minus. These go away. X equals plus or minus the square root of -4. And that's where we've been saying, hey, when you have a square root inside of a negative number inside of a square root, that's where you have an issue, right? And sure enough, that is where we have an issue. This is going to shoot me into imaginary numbers, plus or minus. We know the square root of -1 gives me an I, and the square root of 4 is a 2. So this is 2i. So I get a positive 2i and a negative 2i. So I have 2 imaginary solutions. Each of those is a solution once, but they're both imaginary. Okay. And then this guy's not so bad because we're used to dealing with him. X squared minus 4 equals 0. That's an or. X squared equals 4. No problem. Square root both sides. Okay. X equals plus or minus the square root of 4. And lo and behold, there we have that. 2 real solutions. Okay. So this is where that little bit we keep on saying at most 4 real solutions comes in, because here I just have 2 real solutions. And the reason why is because we see 2 of them are imaginary. So it said give all the solutions and how many times they are. Okay, so x equals 2, -2, 2i, and -2i, each 1 solution. That's my total of 4. Okay, there are no double roots or double solutions in this particular problem. All right. Okay. I don't know why, but for some crazy reason, I did not put any rational functions right here. There should be right here in this, like right after number 9 or number 8, for polynomials, the next thing up we should be talking about is rational functions. And there aren't any, I don't know why, on this review problems. I'm sorry for that. So you need to take a few minutes and make sure you go back and deal with rational equations. We just did these. You just had a bunch of homework on these where you had to deal with vertical isotopes and horizontal isotopes and domain issues and things like that. So go back and look at that homework. I think it's in the Barnett book. It's either 2.3 or 2.4. I think it's 2.4. But make sure you've done that homework and you're good with it. And make sure that you know what causes these things. So remember, just a real quick review. Vertical isotopes happen when you're dividing by 0. Okay, so we can't have those. Remember that. So let's get an example here. I'm just going to give us x squared. Let me do 3x squared plus 5x. This is never good whenever I make this up off the top of my head. I'm sorry, but we'll be okay. Y equals 3x squared plus 5x on the top. And on the bottom, let's do x squared minus 4 because we just did that one. Let's do minus 9. Okay, x squared minus 9. It's never good whenever I make this stuff up off the top of my head. I'm sorry. Okay, so isotopes, vertical isotopes happen when we divide by 0. So remember what you're going to do. Take the x squared minus 9, put it off to the side or down below or whatever. Put your little scratch paper, whatever you need to do, and say it cannot equal 0. I cannot divide by 0. That's a bad spot in the domain. And when I see these rational functions, what makes it rational? There's a polynomial on the top divided by a polynomial on the bottom, right? So when I see these and I've got this variable in the denominator, I need to solve this. X squared cannot equal 9. So x cannot equal what? You got to square root both sides and put the plus or minus, right? X cannot equal plus or minus 3, okay? So what we have is we have vertical isotopes at x equals 3 and x equals negative 3. And remember, those are vertical lines that we do this little dashy thing, right? Okay, so that's how you determine about vertical isotopes. And remember, the vertical isotopes, however many there are, determine how many pieces in my graph, right? So if I only had one isotope, I'd have a piece on the left of the vertical isotope and a piece on the right of the vertical isotope. But here I've got two. So there's going to be a piece over here, there's going to be a piece in the middle somewhere, and there's going to be a piece on the right. So remember, with two vertical isotopes, you always add one. There's one more piece of the graph. So that would be 3 pieces of the graph. Okay, so that's a reminder about vertical isotopes. And then horizontal isotopes. Okay, these guys, there are 3 rules. We're going to look at this one right here. And all it has to do with is compare the biggest exponent on top versus, oops, can't spell exponent, on top versus the bottom. That's all we're doing, right? Okay, so this is the case where the top is a 2 for the biggest exponent. The bottom is a 2, so we ignore this stuff back here. We don't care what's going on. So they have the same degree, top and bottom. And remember that rule. When they have the same degree, all we do is divide the coefficients. So the leading coefficient's right there. This guy didn't have one, so I wrote a 1. We can always multiply something by 1 and not change its value. So that would be, there's a horizontal isotope on this guy at y equals 3. Okay, that's what you know. So remember, there's 3 rules. Some people like the little mnemonic, bobo, Botan eats DC. Okay, if you want that, if you don't like that, go find something else or just remember the 3 rules, okay? So, when the exponent is bigger on top, I'm sorry, exponent is bigger on bottom. Let's go in the order. There's 1 at y equals 0, okay? That's your horizontal asymptote. That's rule number 1, okay? Rule number 2 is when the exponent on the bottom is bigger. I'm sorry. I like to personally do it, do the top first and then the bottom. Okay, when the exponent is bigger on the top, there is none. Oboe botan. Let me do that. Okay, see, I don't even know this mnemonic. Bigger on bottom, y equals 0. Bigger on top, it should be not the same thing. Bigger on top, there's none. Okay. And then the last one is exponents are the same. Divide the coefficients. Sorry, I don't use the mnemonic, but I know it's out there, so I'm trying to help you remember stuff. Okay, so if the exponents are the same, then you divide the coefficients. And it's this third rule here that we used on this guy, right? 3/1. All right. So remember that's out there. It is not on your review. I don't know why I skipped that. I don't know. I'm sorry. Go back and look at your homework on that. Go back and look at the quiz stuff on that. Make sure you remember those horizontal and vertical isotopes because they're going to come up in the next section, which is all about exponents and logarithms, right? So those are the next problems on the test. I don't know why I skipped. Oh, I apologize. I don't know why I skipped straight to exponents and logarithms. So sorry about that. All right, here we go. Picking back up with the review, the practice problems. So make sure you know that rational stuff. Number 9, express in logarithm form. Okay, so it says e to the 6 equals y. And what we're asking you to, when we say express in logarithm form, is to rearrange this so that it looks like a logarithm. Because right now it's in exponential form, right? So we've got e to the 6th equals some number. So exponential looks like you've got a base. Here the base is e raised to an exponent. And we say that equals your answer, right? Okay, so that's what's happening when you're looking at something in exponential form. But whenever we put it into logarithmic form, okay, we rearrange this and we add in the word log, right? So it's log base answer equals exponent, right? And it's literally just rearranging stuff, like writing it in a different format. We're not doing any actual math to it yet. We're just making it look a little bit different so that we hopefully can do something with it. So right now it said express in logarithmic form. You could actually punch this right on your calculator, e raised to the 6th power, and get a value. But we're trying to just work back and forth with converting, basically. We're going to convert it to a log, convert something else back to exponential, that kind of thing. So here we go. Log, that's just part of the format, right? Base, the base is e. Answer, the answer here is y equal to the exponent. The exponent is a 6. Okay. So that's just rearranging stuff back and forth. We're just converting it, right? Okay. So that was A. There's also a B. It says 9 to the 1/2 equals 3. Okay. So rearrange that into a logarithmic format. Log. The base is a 9 of the answer 3 equals the exponent, which is 1/2. Okay, so again, just flipping these around, making sure you can go back and forth from an exponential to a logarithmic. Okay, number 10 is also two parts, and it says rewrite in exponential form, express in exponential form, and we've got log of x equals 7. Now, be careful just for a second because this doesn't have a base on it, right? There's nothing down there. And we know if there's no base written down there, then what we're talking about here is the common log. Okay, so it's always a 10, right? Because we're in a base 10 world. Okay, so rearranging this, we want to put it back into exponential form. So we need the base, which is a 10, the exponent, so this is log base answer equals exponent. The exponent is a 7, right? 10 to the 7th equals whatever this answer bit is. Okay. Log base answer equals exponent. So this is 10 to the 7th equals x. And this is an example of why we use this logarithmic, change it to exponential and back, because sometimes we actually need to be able to figure out what the heck is going on when we rearrange it. This again is something I could just punch that in my calculator. 10 raised to the 7th, it would be a 1 with 7 zeros, right? Okay, so that helps me figure out my value there. B says ln of 4 equals k. Okay, so again, we got to be a little bit smart with these logarithms. Ln, remember that's natural log or logarithm naturel in the French, right? I know I don't have a French accent, but so this is really log base e of 4 is equal to k, right? Okay, so log base e of 4 equals k. So whenever I go to rearrange this, I say the base is an e, the exponent is the k, and equals the answer is the 4. Okay, that's it rearranged. Okay, so I said I'd talk about this E thing in a second. So whenever I come back up here and look at 9 part A, we wrote it as log base E of Y, and that's perfectly legit. It's not wrong. But why I said I'd come back to it is this whole ln thing, right? So we know that when I see something that's log base E, for whatever reason, mathematicians are just lazy, and it's a lot faster to write ln of y equals 6 than it is to write log base e of y equals 6. So it's just a faster notation, and so you can do either one of those, right? Okay. So there's your switching back and forth, exponential to log, log to exponential. We go back and forth and know that how we can use that log base answer equals exponent to convert. Okay. Whew, this video is going to be long. It's getting long here. I'm sorry. Number 11 says rewrite as a single logarithm. And again, you don't have to watch this video if you don't want to. Hopefully, it's just for your benefit if you need it. Log base 2 of A plus log base 2 of B minus 2 log base 2 of C. Okay, so rewrite is a single logarithm. So this is where they're wanting me to use my logarithm properties and cram this all together. And the thing you have to check for before you can do anything is, do they all have the same base? And sure enough, they do. They all have the same base. So that means I can cram these all back together into a single logarithm. That's what it said. It's going to be the same base, log base 2. Okay. And then I can use my exponent rules or my logarithm rules. And again, there's a whole entire review of exponent rules on your D2L now. And I can say, okay, I'm adding exponents here. What did that come from? And remember a quick review. When you add your exponents, it's because these things were multiplied, right? X to the 5th. So these things are separated out, but when I cram them back together, that means they were multiplied. Okay. And then there's this rule that I have this 2 being multiplied out in the front, okay? And so remember 2 being multiplied out in front. When do I multiply my exponents or my logarithms here? That's when it was a power to a power, right? Okay, so x to the 6, 2 times 3. So that means this 2 used to be an exponent here, right? So this was stick a step in here. I'm sorry. Minus log base 2 of c squared. Let me stick that step in there so we can see it. So log base 2 of c squared because I bring this power up here. Okay. And then the last property that I want to use here is this one with the subtraction. And remember, I'm just real quickly over here on the side doing a little bit of work. Whenever I had division, when I was dealing with exponents, that's when I went 6 minus 4, x to the second, and I subtracted those exponents, right? So here, because my logarithms are exponents and I'm doing subtraction, that means that was originally division. So when I cram it back together, that means this guy goes on bottom. Now, it's still one single logarithm, so I'm not going to rewrite the log base 2. Be really careful about that, okay? What we're saying is this AB guy is minus or being subtracted by this C squared guy. So he's going on bottom because he came from subtraction. Okay. So there were 2 videos on exponential functions and 2 videos on logarithmic functions where I tried to work out a lot of these properties for you. Make sure you could do your homework. This is the most recent material for test 1, so make sure that you go back and you watch those videos if you haven't. Make sure you've done those homeworks if you haven't, because again, you just really have to be able to work through this stuff all by yourself. Make sure you can do it. All right. So that was part A. Here's part B. 4 ln of x minus 1/3 ln of x squared plus 1 plus 2 ln of x minus 1. Okay. So I'm just checking my signs to make sure I'm good on my signs. Okay, cool. All right. Same thing here, but I see a lot of stuff being multiplied out in front. This guy's got a 4 out in front. This guy's got a 1/3 out in front. This guy's got a 2 out in front. And all of those, that power rule told me all of those should, if I'm going to cram, directions are the same, express or rewrite as a single logarithm. So I'm going to cram all these back together. So that means I've got to put those back up as exponents, okay? Logarithms raised to a power. So this is ln of x to the 4th, okay? Minus, be careful with this because the 1/3 goes on the outside of the parentheses, ln of x squared plus 1 to the 1/3. That is your exponent for that entire set of parentheses, okay? Plus ln of x minus 1 squared. And hopefully, again, you've been able to do a little bit of review on exponents, and you know when it's a fractional exponent, that means that this guy came from inside of a radical, right? A square root, or in this case, a cubed root. When it's a fraction, that's what happened. That's how we got there. Okay. Now that I've gotten rid of that multiplication out in front, I'm looking at all of these going, is it the same base? ln, ln, ln. Yes, they're all base E. So now, yes, I can indeed cram all of these things back together, which is great. Okay, so which one goes where? Here I've got subtraction, and we know that the first guy goes on top and the second guy goes on bottom. So again, this is one big logarithm, so ln of the stuff. And on top, I've got an x to the first. On the bottom, I've got x squared plus 1 raised to the 1/3. Okay. And this guy, I think sometimes people can get confused. He's a plus guy, right? Okay. Whenever I was plussing, I'm multiplying, but sometimes people will be like, oh, this goes on the bottom multiplied. That's not true. Okay. If it was all on the bottom, there would be parentheses around all of this, right? But there's not. So this guy, remember, you can rearrange addition, right? So I didn't have to write it like this. This guy could be right there. So he is actually being multiplied and he is actually on the top. Okay. So what do we have? X to the first times x minus 1 squared all over x squared plus 1 to the 1/3. And again, there is that one last step you can certainly do. X to the fourth times x minus 1 squared. And say, hey, that's a cubed root. The 1/3 is the same as a cubed root. Okay. And again, we'll see more with those fraction exponents, a lot more whenever we get into derivatives. So I want you to start being familiar with those. I don't want them to freak us out. I don't require that you change this into a cubed root right now. By the way, I've done a couple of cubed roots and I haven't put plus or minuses out there. I hope everybody's okay with that. Why am I not putting a plus or minus out here? Because this isn't an even root, right? We only have to do that plus or minus stuff when I have a square root or a fourth root or a sixth root. This guy's a cubed root, so I can do stuff like -1 times -1 times -1, do it 3 times and get a negative answer, okay? So that stuff happens here. No worries. The problem would be whenever I have a plus or minus, would come whenever I have an even square root, fourth root, so on. Okay, so either one of these is acceptable. I'll take either answer. You're good. All right. It's 11. Moving on. I'm just trying to get through a lot of this stuff so you can see it and see the worked out solutions and be okay, I hope. Okay. Normally, I would spend about an hour and 15 minutes or more going through all these problems in a class. Number 12 says solve the equation without using your calculator. 2 to the x plus 1 equals 16. Okay. The idea here is hopefully you can look at this and say, without using a calculator, and I'm also not taking a logarithm here, right, to get this x out of the exponent. That's what I would want to do is get that x down, but I'm not doing that. So what else can I do? I'm going to focus on the 16. And hopefully everybody knows that 16 is the same as 2 times 2 is 4, times 2 is 8, times 2 is 16. So 2 to the fourth power is 16. That's just a little side note. Okay, it is a perfect fourth power. Okay. All right. And the idea here is, hey, once you see, I can rewrite this so that they have a common base. Both of these are 2's on the bottom. If the bases are the same, what did we say? Then the exponents are the same, right? So we can pull these guys down and say x plus 1 equals 4. Basically, we can ignore the bases because if those are the same, right? So I don't have to worry about 2 equals 2. What I'm worried about is this guy with a variable in it, right? So subtract 1, x equals 3. Okay. So let's just check it real quickly because x equals 3. 3 plus 1, that's a 4. 2 to the fourth equals 16. Yep, that's right. Okay, no worries. So that's what we mean by don't use your calculator. I didn't have to use a calculator there. I'm just using properties of exponents that I know. Okay. All right, 13 has a bunch of parts. It says solve for x. A says 2 to the 3x equals 34. Okay. Solve for x. And it doesn't give you any kind of thoughts on how to do that. So whenever I look at this guy, I go, oh my gosh, 34 is not a power of 2. So I can't do what I just did a second ago. 16 times 2 would have been 32, right? Then I'd have 2 to the fifth. But 34 is not a power of 2, so that's not going to work for me. I can't do what I just did. And I see that my variable is in the exponent, and I want it down from there. So I'm going to convert to logarithms, okay? So log, the base is 2 of the answer equals the exponent, okay? Log base 2 of 34 equals 3x, okay? Now, some people want to get an actual number value for this, and if you really know how to use your calculator, you can. You can get this, but it's going to be a crazy decimal, and I just don't want to deal with it. So I'm literally going to say all you have to do is solve for x, okay? Divide by 3, x equals log base 2 of 34 over 3. And leave it alone, okay? Your calculator doesn't naturally do base 2 stuff. It does base 10 and base E because those are the two that are programmed into it. You can force it to do some log base 2 stuff, or if you watched the video, I think I had one out there that was about changing the base. Here you can do log of 34, log base 10 of 34 divided by log base 10 of 2. Okay, so there is a change of base if you want to do that, but I don't care. Change of base formula. It's probably on your formula sheet somewhere, but I don't care about that. I just want you to get to this point. If you get to this point, I'm going to be like, woo, they did so good. I'm going to be so thrilled with you because that is amazing. So if you get that far, you don't muddy the waters is what I try to say. Don't make it harder on yourself by, trying to do more and more stuff. We don't need a decimal. We don't need an approximation. This is an exact answer. Okay, exact. I like it. We don't need 5.29 or whatever it is. Okay, so don't do that. Leave it alone. Okay, this is not 12b. This is 13b. What's wrong with me? 13b. Okay, 13b says log base 3 of x equals 4. And again, it just said solve for x. It didn't tell me how to do that. But again, I see the x is inside of the logarithm here. And I think if I rearrange this, I can get the x out of the logarithm. Sorry, I had to grab a drink. Okay, so I think I can rearrange this and convert it to an exponential format. If I do that, remember the exponential format is your base, which is 3, raised to the exponent, which is the 4, equals your answer, which is an x here. And sure enough, we can do that, right? 3 times 3 is 9, times 3 is 27, times 3 is 81. So here we've got x equals 81, and absolutely we're done, okay? So just rearranging this, just being able to convert back and forth, that's really important here. And I think it will pay off for you if you know those two, how to convert back and forth. Okay, solve for x, and they just give me, I think that's a 5. Log base 5 of x plus log base 5 of x minus 4 equals 1. All right. So these guys have the same logarithm base. So that means I can cram these back together. Again, it just said solve for x. It didn't give me any kind of direction, but whenever I see the variables inside of the logarithm, I really want to convert it back. Okay. I really want to do my conversion stuff. I can't do that with it spread out like this. It's got to be one single logarithm equals some number. So if I have log of something equals something, okay, no matter what the base is, yes, I can use my conversion, okay, convert to exponent, right? Because it's log base something equals something. I can totally switch it back around into an exponential format, okay? But this won't work for me, so don't just jump in there. You've got to use these properties, okay? So I've got a log base 5, but who cares as long as they're the same, plus another log. And remember, addition came from multiplication. So before these were split out, or if I want to cram them back together into one logarithm, I got to multiply. x times x minus 4. And remember, when I cram them back in together, there's only one log base 5, okay, equals 1. Okay, I'm going to have to do something with that because I can actually do the mathy stuff there. So let's do that. Log base 5 of this is x squared minus 4x equals 1, and that's cool. Now I have log of base something of something equals some number. Now I can do what I want to do, which is convert. Okay, so the base convert. The base is a 5, the exponent is a 1 equals x squared minus 4x. The answer. All of this is the answer, right? Log, base, answer equals exponent. So I rearrange base to the exponent equals whatever that answer stuff is. It's all together. Oh, excuse me. Okay, so here we are. That's looking good. I like it. I can solve this guy. Let's move the 5 over. 0 equals x squared minus 4x minus 5. I really hope you can factor by now. If you can't, you're just going to struggle in this class, and I don't want you to struggle, so that's what I'm worried about. Factors of 5, one's a positive, one's a negative, and they add up to negative 4. I think we're going to have x squared plus an x minus 5x gives me negative 4x. That's good. And then 5 times 1, negative 5 times 1 is a negative 5. Okay, so factor that guy out. Set them both equal to 0. 0 equals x minus 5, or 0 equals x plus 1, right? Solve them up. X equals 5. You've been doing this solve for x since the very first day. X equals negative 1. So you ought to be able to do that set it equal to 0 and solve thing pretty quickly. The only thing I'm going to caution you on, let me pull this down just a tiny bit. I'm sorry, it's not going to all quite fit in there. The only thing I'm going to caution you on is remember that we started with logarithms here. And if you remember, the original graph of a logarithm looks something like that, right? Before I shifted or do any transformations. So I got to think about, I can't put a negative number into a logarithm. I wasn't worried about this on the last problem because this was 81, positive number, and this was just log base 3 of x, so log base 3 of 81. But here I'm a little bit concerned because not only I can't put negative 1 in here because log base 5 of negative 1, that's going to give me an error, right? Because it's not on my graph. It's over here in the no man's land that I shouldn't be in. So for sure, this negative 1 guy is not going to work. Okay. So now we get to the point when we're looking at logs that we say we have to check those answers. Okay. We haven't been having to check our answers, but when I have a log of a negative number, that's not going to work. Okay. The only time that would work is if this graph had been shifted, say like that, and the vertical asymptote was shifted, then okay, maybe I might be able to have x equals negative 1. I have to check. The problem here is log of negative 1 just doesn't work, right? So that's not going to work. But also be careful because I have a positive answer here, and you might go, oh, that works, no problem, it's a positive. And most of the time that's true, but let's just check it real quick. X equals 5. Okay, log of 5, we're good. Log of 5 minus 4 is 1. It's also positive, so we're good there. But just think, what if I had had 3? Log of 3 minus 4 would be negative 1, right? And if that had been the case, it wouldn't have worked. And even though 3 was positive, when I plug it in, I'm getting a negative answer. That would still be bad. So 5 does work. 5's okay. But like I said, you have to check on these logarithms. If it was a 3, I would be in trouble. So don't just assume, don't just assume that that is going to work. You have to check, okay, on these logs. Okay. Is everybody all right? I'm almost at the end of this video, I hope. Hold on just a second. All right, sorry about that. I dropped my papers on the floor. I had to dig them all up and put it together. Okay, one more of these. Solve for x. It doesn't give me any direction other than that, so we really got to think about it a little bit. Log base 3 of x squared plus 1 equals 2. All right. Now, this one's kind of set up nicely for me so far because it's just a log equals a number, so I can convert. Make it into an exponential. 3 squared base to the exponent equals the answer. Remember, all of this is my answer. X squared plus 1. Hey, that's kind of nice because that's just 9 equals x squared plus 1. So let me subtract a 1 off. X squared equals 8, right? Because 9 minus 1 is 8. So I'm going to get an answer pretty fast here. Square root both sides, plus or minus. X equals plus or minus the square root of 8. Okay. And so I'm getting two answers, that plus or minus gig coming in because I took a square root. And I want to check these because I'm here going, ooh, square root of 8. Let's see, that's not quite 3, but if it was negative, I'd have a negative 3, right? So you really got to be careful. The nice thing about this one is when I put in negative square root of 8 squared plus 1, what happens? Negative times a negative is a positive, right? So this becomes the positive. Square root of 8 squared is 8 plus 1, right? So inside of the parentheses here, even though I started with a negative number, I now have a positive number because this negative number being squared here, we're okay. But you can't just assume that's going to happen, especially I see that negative and I go, oop, oop, warning, Will Rogers, warning. You gotta be careful here. So double check, make sure it works. This one does. We're okay. All right. 14, use your knowledge of log properties to solve the question. Log base 2 of x plus 11 plus log base 2 of x plus 7 equals 5. I've done 2 or 3 of these now. I feel like you should know what you're doing, so I'm going to pause it and work it out, and I recommend you pause it and work it yourself, and then we'll just come back and see the solution. So go for it. Okay, so I have this thing worked out. I'm using the property from the logs where it says if you're adding two logs, they must have had the argument inside must have been multiplied. So I put them together. I multiplied them. Log base 2 of this stuff equals 5. I went ahead and multiplied that guy out. So you ought to be able to distribute those through FOIL, whatever you want to think of it as. I've got that multiplied out and worked out. And now I've got I combined my like terms. Log base 2 of the stuff equals 5. And I say, hey, now I've got a logarithm equal to a number. So I convert. 2 to the 5th equals all that stuff. 2 to the 5th is 32. I subtract it. I've got 45. Hopefully you've done all this. If not, pause it because I'm working through it really fast. Factor this. Again, hopefully you can factor really fast. You're not having to go to quadratic formula, but if you are, that's fine. Quadratic formula will work. It's just going to take you a lot more time. I got x equals negative 15 and x equals negative 3. And automatically I'm like, oh no, both of my answers are negative. I might be in trouble. So let us go back up here to the logarithms and see. Plug in negative 15. Negative 15 plus 11 is negative 4. So if I plug in negative 15 here, I'm going to be taking log base 2 of negative 4. And what do we think about that? That's not good. It's not going to work, right? Okay, same thing here. Negative 15 plus 7, also negative. It doesn't matter if it works in both. If it doesn't work in either one of them, it's not going to work. So that guy's not going to work. Okay. Now x equals -3. Again, still a negative, but whenever I do -3 plus 11, what do we think about that? That's a positive 8, so it's okay there, right? And same thing's going over here. -3 plus 7, yeah, it's a negative number, but when I plug it in, I get a positive 4, right? That's okay. All right, so then you can get a negative answer. X equals -3 here actually does work. It's okay, but it works because of this adjustment step that's inside of the logarithm that's going to make me be taking a log of a positive number. Even though I'm putting in -3, once I do this arithmetic in here, I'm taking the log of a positive number. So it works. X equals -3 is your answer there. X equals -15 is not. It doesn't work. It's an extra solution. We have to check our answers and make sure we know that guy's not going to work. He's got to go away. All right. 15. I'm going to do the same thing. Use your knowledge of log properties to solve the following. I just don't want this video to be 2 hours, so I'm trying to hustle with it. ln of x plus 1 minus the ln of x equals 2. Again, I see I've got two different logarithms equals a number. I can't convert yet, so I'm going to push pause. I'm going to tell you to go do work this problem out. I'm going to work it out, and then we'll come back real quick. All right, so here we go. Those are two logarithms. They have the same base, and they're being subtracted. So I used my property that says I can divide those arguments, dump them into one logarithm. The first one divided by the second one equals 2. Now I have a logarithm equals a number I can convert, okay? E squared equals, because the base was e base to the exponent equals all that argument is the answer stuff, right? Now I'm looking at this going, ooh, I'm kind of in trouble because I've got two different x's in here. And this is where your algebra skills are really going to come in handy here. I want to clear the denominator. And to do that, I multiply by x over here. That's going to give me x plus 1 dropping down right there. And whatever I do to the right-hand side, I have to also do to the left-hand side. So we've got x times e squared equals x plus 1. Okay. Now I'm not liking the way this looks because I've got an x over here and I've got an x over here. And I just need to get those together on the same side. So I subtract the x over equals 1. And now I say, I got x in two different terms. I need to factor that x out. So this is maybe a thought process to go through. If I divide an x out of this first term, there's an e squared left, right? Get rid of the x. If I divide an x out of this term, factored it out in front, what's left over? That x goes away. There's just a 1, -1, right? Okay. So that means this is what I got. I want the x by itself, so I'm going to divide both sides by e squared minus 1 because that will get the x completely by itself. Remember, that's your goal. X equals 1 over e squared minus 1. That's my answer. Okay. And then just in case you're wondering, be careful. You still need to check this answer. I've got an x plus 1. That's not going to mess me up unless the x value is negative. But here, again, if the x value is and bigger than 1, if the x value is negative, I can't take an ln of a negative number. So we just need to evaluate this for a second. E, we said before, is a positive value. It's like 2.7, right? 2.72. And if I square that, that's going to be positive value. And if I subtract 1, that's going to be a positive. So this is going to give me a fraction. And that's fine. The real deal is it's a positive fraction, right? So let me show you that. I'm going to use my E button. Okay. It's on top of the ln. The ln is the button. E the x is there. So I have to use second. E to the second power is what we're dealing with here. Sure enough, that's 7.389 Even if you subtract that 1, you're okay. So what this is 1 over 6.389. That's a decimal approximation, but it's definitely positive, right? That's what we care about. So put in a positive number here. We're okay. No problem. All right. Okay. The last 1, 2, 3, 4 problems on this. Remember, you're not doing 20 through 24, right? So the last bit of this is all word problem-y type stuff. You invest $700 at 6% compounded quarterly. How much money are you going to have in the end of 2 years? That's what we're after. $700. And remember that because we're using compounded quarterly, we're going to use that formula. A equals P times parentheses 1 plus R over N raised to the NT. That formula is going to be on the formula sheet for you, so you don't have to remember it. You're just going to use it. And here we go. We want the amount at the end of 2 years, so we're trying to solve for A. What's the principal? P is principal. That's the amount I put in, right? 1 plus what's the interest rate? The interest rate was 6%. How do I write that in my formula? 0.06. Yeah, 0.06. We move the decimal 2 places. The N, number of compounds, and we said quarterly. Quarterly means 4. 4 quarters in $1, right? So 4 compounds. This is the same N. And what's my T? T is time in years, so that's a 2. Okay. So, and again, I hope that you can come up with that formula, find it on the formula sheet, figure out what goes in about as quickly as what I just did there. Okay. If you're really stressing out, trying to figure things out, what's the R? I don't remember what the N was. It's going to take you too long. You need to be able to do these things pretty quickly. So this is 700, 1 plus some number, and then 4 times 2 up here. The exponent's going to be an 8. I just need to figure out what's 0.06 divided by 4. This is a situation where we're going to deal with decimals. Okay. We're going to do the approximation. So this is a 0.015 plus a 1. Raise it to the 8th power. Okay. So this is A equals 700, and I have a number for this stuff. 1.12641. I'm sorry. 1.12649. Okay. And actually it keeps going. If your calculator goes more decimals than mine, that's fine. You don't have to write them all. Just keep the decimal in your calculator so that now we can say all of that stuff times 700. And that way I'm not going to have rounding errors, right? Or not as many at least. So my answer is $788. And be careful with this. It's a 0.54. The 4 is followed by an 8. The 8 would bump this guy to a 5, and the 5 would bump this guy to a 5. So, and we're dealing with dollars, amount in the account, right? So I would go to 2 decimal places. I think it's 7088.55 cents. Okay. So for these word problem-y type things and using these formulas, which is what we've got, there's like 4 problems here about this. I hope you can work through them pretty well and not needing a lot of help from me. So go ahead and do the next one. How long does it take to double $2,000? Okay, so that means I'm putting in $2,000. What's the double of that? $4,000 is what I want at the end, right? Double $2,000. If you invest it at, 12% continuously compounding. Okay. So what that means is I lose my n, right? I don't need to deal with number of compounds anymore because it's a continuous compounding, and that's a different formula. If you'll remember, A equals P e to the RT. This is where that exponential stuff comes in with the e, with the natural logs and all that kind of stuff. That's why we care about him. Or one of the reasons why we care about him. He comes in more as you go in through calculus. So the E here, remember, is not a variable. That's the number. It's like 2.7. We're going to use our button on our calculator. So anyway, we want $4,000 and we're going to put in $2,000. The E, the rate is 12%. So that's a 0.12. And the question was, how long does it take? So we're trying to solve for T, right? So if you're not aware of this, this actually makes a lot of difference. That T's in the variable, e to the something, that's an exponential function, and we need to get that T down. So hopefully you remember that's why we have logarithms, right? That's what we're going to do with this, okay? Anytime I do one of these doubling things, so I need to get the e to the thing by itself before I can do my logarithm. But whenever I do this and divide by 2,000, this becomes a 2. That's the double 2 times 2, right? So you could have kind of shortcutted that, cheated a little bit, and said, I'm not going to do that. I'm just going to say 2 equals. That's fine. All right, now I have some number raised to a power equals some number, base to the exponent equals answer, and now I'm going to use my logarithms. I'm going to convert, but this time going the other direction, right? Log base E, which is ln, of the answer, which is 2, equals your exponent, which is the 0.12 times the t. Okay. Log base answer equals exponent. All right. Now I've got this guy. I'm good. Divide by 0.212. T equals ln of 2 over 0.12. I am perfectly happy if you just leave that answer just like that. The less messing around with it you do, the less likely you are to make a weird mistake. Okay. But I do understand that you can come up with a number for this because your calculator does ln, right? So natural log of 2. So this is really 0.69315, whatever. Divide by the 0.12. Now, just a second here. I'm taking a decimal. I'm dividing by a decimal. What happens when I divide by a decimal? It tends to make it bigger, right? Okay. When you divide by 1/2, it's like dividing by 0.5. You have to invert and multiply, and it's like doubling it, right? So when I'm dividing by 0.12, I started with 0.69, but now I'm a lot bigger, right? 5.776. Okay. And I'm going to leave that guy alone, and I use the squiggly equals. It's approximate because that's a decimal. Remember, this question was, how long does it take this thing to double? That's 5.8, almost 6 years. Okay. That's what we're looking for there. Okay. All right. I feel like this is dragging. I'm sorry. Again, you don't have to watch this whole thing. If you feel good about it, just skip on over. Number 18 says you're going to put $6,000. We only have one more after this, so we should be good. $6,000 for 5 years. It's going to be invested. Which account would yield the greater payoff? So I'm actually going to let y'all work this one. I'll pause, I'll work it, and then come back and see if you agree with me. A says we're going to do 7.25%, and it's going to be compounded monthly, which means what for the number of compounds in a year? 12, because there are 12 months, right? Okay. And then B says 7.0%, but it's going to be compounded continuously. Okay. Which means continuously. Yeah, there we go. Which means you're going to have to use PERT, right? Okay. So, two different formulas, use them, come back and see if you got the same answer as me. And the question says, which one gets you a better yield, right? Greater payoff. Okay, hopefully you worked it both ways and you've got this working out. Most of the time, compounded continuously, if it was the same percentage rate, compounded continuously would be better, right? But what we find here when we work it out, if you need to pause and look at my math and see if your math matches my math, hopefully my math is right. I do have a little bit of a rounding thing here at the end. I tried to keep it in my calculator and then multiply by the 6,000 at the end. But what we see here is $8,600 from the compounded monthly and $8,500 from the compounded continuously. And the reason why is because even though the compounded continuously is compounding quicker, and it does it more often, this is 0.25% of interest. That's more for the compounded monthly. So this is one of those things that kind of comes up as you start looking at business loans and moving forward. If you're trying to do an amortization on a house or something like that, where you go, ooh, you know, um, which compounded continuously might be better, but which one is going to have a better effective rate? What's my better payoff going to be? And in this case, it was compounded monthly. Okay. And then the last one for this, because we're not doing systems of equations right now, is number 19. Just hold on to those systems of equation problems for later. 23, 24. Again, we didn't do this semester, so we will do it at the end of the semester. I moved the content around. Okay, number 19 says the number of bacteria is in a culture at a time, T, which is in hours, obeys the law of uninhibited growth of, and they give you the formula. N of t equals 1,000 e to the 0.01 t. Okay, and if you remember, this is very much like the PERT formula. Okay, where this is like the initial number of bacteria that we're dealing with. E is the natural number here, so 2.72. And this is the rate of growth. And T, and they said, is my time in hours in this case. Okay, so answering the following questions. And I just basically did that for you. So the initial amount of bacteria. That's your P, right? 1,000. Okay. B says, what's the growth rate of the bacteria? This is like PE to the RT. Here's my growth rate, 0.01. Okay. Or what is that as a percentage? Think about your decimal, right? 1%. That's a 1% growth rate. Okay. C says, what's the population of the bacteria after 4 hours? So I want to know the number of bacteria after, oh, I didn't put in the 4 here. 4 hours. So T is a 4 here. I don't know that. You're not going to know that. We're going to totally use our calculator. That's why we have calculators. 0.01 times 4. That's my exponent, right? So I'm going to do E raised to the, and I'm just going to put in 0.04 because that was what that is. Okay, that's this number. You don't have to write it down. I'm just writing it down so everybody knows this number is right there. Okay. And whenever I multiply it by 1,000, it's going to move the decimal place, right? 1040.81. Okay. Remember, that's the number of bacteria after 4 hours. So we started with 1,000, and after 4 hours, we have 1,040 basically. Okay, and part D says, when will the bacteria reach 1700? Okay, and you're going to find it's actually going to be pretty quickly because this is that compounding continuous formula, right? So at 4 hours we've only added basically 40 bacteria, but now that compounding thing's going to come in, right? So it's going to go fast. So here they want the number to be 1700. So I'm going to plug in the 1700 on the left-hand side here. That's what they're asking me for. And they want me to find how long. So they want me to know the time, right, in hours. So I'm going to solve for t. We know this is an exponential thing, and the t is in the exponent. So for me to get it out of there, I'm going to have to take a logarithm, right? Okay, so that's my process. Just letting everybody know before I do it. 1700 equals 1000 e to the 0.01 t. That's the formula we were given, right? I can't do anything until I get this exponential guy by himself. He's being multiplied by 1000. So I'm going to divide by 1000. Okay. And I'm going to see things go away. So this is 17 divided by 10, or 1.7, equals e to the 0.01 t. If you don't believe me, 1700 divided by 1000, 1.7. So we are good. And now I have an exponential guy sitting equal to some number, so I can convert. That's what we want to be able to do, hopefully. And now I say, oh, this is an exponential. I need log base, e in this case, log base answer 1.7 equals the exponent comes down, right? 0.01 t. And like I said, we're trying to solve for t. We want to know how many hours. So I'm going to get the t completely by himself by dividing by the 0.01. T equals the ln of 1.7 divided by 0.01. Okay. And notice, by the way, that the ln of 1.7 was already over there. This is all divided by 0.01. We are not using one of those logarithm rules where I subtract inside the logarithm, right? That's not what this is. I got this guy by himself. I'm sorry. I got this guy by himself. I had the exponent. Now I want the t by himself. So I divide both sides, the entire side, by 0.01. Okay. So let's see what that looks like. The ln of 1.7 equals some decimal. Divide by 0.01. Again, what happens normally whenever I divide by a number smaller than 1? It should get bigger. There it is. So sure enough, I've got 53.06. Let's call that a 3. So bigger, more than 53 hours for this guy to come up to 1700, which is almost doubling. But when you think about that, hours. Seems like a bigger number, but when you think about that, 53 hours is just a little bit bigger than 2 days, right? So your bacteria here are really growing fast in the first, like in 2 days, it's a lot bigger than what you started with. Almost double. Okay. So that is the 19 questions off the practice exam. Lots of parts and pieces. Remember to go deal with the rational expressions. Make sure you got those vertical and horizontal isotopes down. And if you can do this on your own, I feel like you should be able to do at least 85-90% of the test with no problems. Okay. So make sure you're in there and let me know if you have questions. Good luck.